Little training. Okay. I won't walk in front of the projector screen again, I think. So welcome, everybody. Again, I'd like to welcome everyone to WPI. I know Chris did upstairs, but at least I assume he did upstairs. But as you know, I wasn't there because I was trying to find my computer. I had a moment when we were, a few minutes away from me speaking, saying, well, I better go downstairs and set up my computer. Where did I put it? And the last time I remembered seeing it was taking it out of the hatchback in the car, putting it on the driveway, and putting something else in the car. And couldn't remember if I ever put the computer back in. I did. It was in the car. We're good. You know, I've done things like that before, too, and it wouldn't have been that bad. I've already ordered a new computer. But the slides for today were only on this computer. So it may have been inconvenient if I had to use like a sketch board and draw the things, but I think I could have done it. I talk for a living. This is what I do. So I think I could have pulled it off. Again, welcome everybody. You'll see plenty of me throughout the week here, especially if something's going wrong. My main role today is troubleshooter, which I don't know why they put me in the first time slot if I'm troubleshooting, but I'm going to talk about measurement and characterization of directionality on topographies. People talk about anisotropy and isotropic surfaces. And although this is my doctoral work, I can never get those words straight in my mind, maybe because it's my doctoral work. So I prefer to think of directionality because this sort of has a meaning to me, a physical meaning to me, whereas anisotropy, this would be the and, so this is sort of negating it, right? So against isotropy, against direction, right? So anyway, the words are confusing to me. So I'm going to use directionality. I may throw in a little anisotropic. I think I know what it means. I'm not certain that I know what it means. So we'll note to the troubleshooter that we need to work on the projector thing, but I have the technology. Maybe. No, I'm just not in the right window. Ha. I declare victory. Okay, so measurement, characterization, directional topography. So when we talk about directionality on a surface, I took this actually from a paper by Walski et al., published in 2010. So I took his figure here, and a surface like this is sort of considered to be non-directional. So that would be isotropic, right? Isotropic. This would be anisotropic. This is directional. And it's sort of got a clear direction. So any person looking at the surface, in the US standard, we would call that the lay. So the scratches are all lined up in one direction. And then this one, well, is this anisotropic? Is it isotropic? It's commonly referred to as multi-directional. And so this was great. I started actually looking at this about many years ago. 1999 or thereabouts was when I first encountered this sort of directionality. And this was, it was actually how I became involved in surfaces. So I'll digress a little bit and talk about that. But in 1999, I was a new graduate student here at WPI. Professor Brown had found some free tuition for me, so he was paying for some of my credits. And in exchange, and he found me a summer job. The summer job was going to be using some instruments that we had here to make some measurements for some various companies. I think the company we started out with was 3M. So 3M makes Post-it notes. They also make pavement marking tape. It's beneficial to them that the pavement marking tape adhere to the asphalt pavement. So they're trying to understand how their marking tape adheres with pavement. We had done some work with them, or Chris had done some work with them in the past, and they wanted to acquire their own instrument for measuring asphalt pavement so that they could go make some measurements on the pavement, correlate the adhesion with the surface measurements. They wanted to benchmark the instruments they were looking at by using the instrument at WPI that they'd previously used to do this research. Makes sense. So my job, summer job, I'm going to do some measurements. I learned how to use the instrument. I had about 15 minutes worth of training. Set the asphalt pavement samples under it, press go, Find out that it's crashed. Okay, I learned how to use the instrument again with another 15 minutes. So I made the measurements finally after a few false starts. We sent them off to 3M, and then I moved on to the next task. Well, a few weeks later, they were doing analysis on the software, and they are on the measurements we sent out to compare with their instrument, or the one they were looking at. And they said, when we take your measurement files and we turn them 90 degrees in software, and we rerun the analysis, we get different answers. And pavement should be isotropic. Pavement surface shouldn't have any direction. So there must be something wrong with your instrument. So we did tests, and we did tests. And we said, well, the pavement probably wasn't isotropic. It probably was anisotropic. If you look at the nature of how the asphalt pavement is made, it's made by a machine that moves along in a direction. So there probably is direction in that surface. Whether or not it's important to you is different. But sure enough, if we took any surface and we turned it 90 degrees in software, we got different results for the analysis method that shouldn't care about the direction on the surface. So this turned into a master's thesis for me, and now next May a doctoral dissertation for me. So 3M was good to me. We were able to show, actually, and I'll show some of that, but it got me, so 1999, this paper here, Walski et al., they came out 2010, and they looked at methods for characterizing directionality on the surfaces, which is why I bring this up. In 1999, I started working on this. About the same time, Tom Thomas published a paper, and I've got some little move to my other job of troubleshooting. Maybe. Maybe. That just went back to the first slide, huh? Okay. All right. So Tom Thomas noted that surface roughness is an isotropic phenomenon. In fact, people think surface roughness is an isotropic phenomenon, like the guys at 3M. In fact, the process that made it, so he's talking specifically about machining process, but I'd look at most manufacturing processes are directional in nature, and they go along with surface properties. We don't need to see his figure 1. Why do we care? I sort of... Sorry about that, I got off on a tangent, but why do we care about the directionality on a surface? So processes that make surfaces tend to be directional. So things that interact with our surfaces can be influenced by the directionality on the surface. So the thing I like to look at is, for example, if you have two surfaces that have to interact with each other. So say they have to interact with each other in such a way that they're going to keep a fluid on one side, so make a sealing surface. If we do that, what should the surface look like? So as we get to being the designer, and we're wondering what should our surface look like, should we make two smooth surfaces and push them together? Should we make two rough surfaces and push them together? Does anybody know the answer? I originally made these slides for a class that I was teaching.
Another question by me again?
So if I need to make a sealing surface,
yes.
So I'd like to have two surfaces that are interacting with each other.
Yes.
I'm going to have fluid under some pressure on one side of it, and I'd like to keep it on that side.
So assuming laminar flow, you want to minimize the gap distance H.
Well, I'd like to have no flow, though, right?
You'll never have no flow.
Okay.
You can minimize it.
All right, so he wants to minimize the flow. All right, so, and we're going to assume laminar flow because it makes the math easier?
Yes.
Okay, so you want to minimize the gap between the two surfaces.
And so the gap would be like the minimum height of one surface minus the maximum height of the other, but I may have my signs misplaced.
Okay, but I think we all understand, so minimize the gap, so reduce the amount of space between the two surfaces. So if I have two surfaces, if I draw, So two Euclidean surfaces. And we want to minimize the gap between them by applying pressure. Right? Some force on them will help us minimize that gap. And then we're going to have the least amount of flow between them. Now what if...
And surfaces are never flat, even though...
Ah, yes, of course. Yeah, we're all here, so we understand that. So when I superimpose my roughness on my ideal Euclidean surface here, does the direction of that roughness matter? So, because we don't have two lines that we're pressing together. We have two plus dimensional surfaces that we're pressing together. So if we had some texture on here that's lined up in this direction, long troughs, it would be harder to minimize that gap, because as the two peaks push on each other, they may deform a little bit. In fact, we hope they deform. There's going to be a channel that goes through there. If I turn the surfaces 90 degrees and my scratches are against the direction of flow, you would think we could have a better chance at sealing, because at least when we've minimized the gap, there's a longer path for that fluid to get through as it goes through the sealing surfaces.
If you only turn one, then you've made it portable. If you have two,
yeah, I could see that. All right, so we'll stipulate that we care about the direction of surfaces, at least in the case of sealing surfaces. All of our energy somehow has to deal with a sealing surface, so all energy we use in the world. Would you agree? You work in the energy field, right?
We have a lot of tricky sealing surfaces.
Yeah. So, okay, so in perhaps the most important industry in the world, or the largest industry in the world, which is making energy that everything else consumes, sealing surfaces are important, and directionality is important for sealing surfaces. Okay, that's why we care. Next slide. Oh, it's changing them down here. Okay, so we have standards that characterize surfaces. And in fact, the US standard, surface texture, surface roughness, waviness, and lay. So lay is in the title of the standard, so it must be important. And in fact, the standard tells us how to characterize lay. So it's the predominant direction of the surface. We talked about that already. And there's a whole page in the standard dedicated, so 120 pages in the standard. There's a whole page dedicated to how we characterize directionality on the surface. So you can say at the design stage, I would like the machining marks or the forming marks on my surface to be lined up sort of like this. I'd like them to be lined up sort of like this. I'd like a crosshatch pattern. So it's problem solved. The designer can say what he wants. You can't put a number next to this, though. All you can do is this. It's a little bit better in the ISO standard because they don't have a whole page dedicated to it. Ooh, is that not on there? The ISO standard says measure the surface in the direction of the highest RA. So that's how you're going to characterize the surface, but there's no method for quantifying what is the direction on the surface. So at the same time I started looking at this, Thomas was looking at it. Thomas came out with the idea that you could use the complexity of the surface to characterize direction. And at the same time we did that, so we looked at the complexity on the surface. People know what I mean when I say complexity on the surface.
No, not precisely.
Not precisely, okay. This talks about how we can measure surfaces. I'm going to skip through that so we get ahead. All right, so when we're looking at complexity on the surface, one of the ways you could measure this is you could extract a profile from the surface, and you could say, how long is my profile? And there's the famous, how long is the coastline of Britain? Well, it depends on how big the dividers are when you measure the map, right? So this comes from Richardson when he's talking about how long is the coastline of Britain. So what we did is we applied this to looking at surface profiles extracted. That is not a seat. And if you take different lengths of dividers, like Richardson did when he was looking at the coastline of Britain, if we take different lengths of dividers, we can compare the total length of our dividers as we add them together. So the length of that surface compared with the projected length of that onto a flat plane. And when we do that, we do a bunch of different dividers. And when we do that, if you plot the length of the dividers, we call that the scale, versus the relative length, so the projected length, on a log-log plot, you get a graph that looks typically like this. This one is kind of special. This is actually a turned surface in steel, so you can see that there's this periodicity in the surface. These peaks, local peaks along here, are factors of the period on the surface, so we can find the periodicity on the surface. If that's all you care about, use an FFT analysis. But it's an artifact in here. But we typically get a long region, so this is 1, 2, 3 decades long of a linear fit here as we get down to the finer and finer scales on the surface. So if we look at the complexity from profiles taken in this direction and compare it to the complexity of profiles taken in this direction, these profiles are more complex. And so now we have two numbers. We could say that there's this ratio of complexity in one direction to the ratio of complexity in the other direction. So now we can quantify how much direction is there on the surface. Taken further, if you take profiles like that from the surface and you go out in, say, well, the idea was to go in all directions on the surface. So if you go in all the directions on the surface, and then you see which direction has the highest complexity, and you could plot the complexity versus direction, you can now characterize a directionality on that surface. And that work we did back in 2006, which ended up nicely for us. We did it in conjunction with some anthropologists at University of Arkansas. And that ended up getting published in Nature, and it was a great way to show the method. In 2010, when Walsky was looking for ways to quantify directionality on the surface, I was very disappointed that what drew me to his paper was that he didn't cite my work. It turns out he was looking in engineering journals. He wasn't looking in anthropology journals. So one of the problems with our analysis method is we've only published it in the anthropology journals. We haven't published it in the engineering journals, which is nice about having this meeting. We actually had to get a little bit more nuanced than just looking at so if you take the analysis in all the directions on the surface here, you end up having to interpolate points, right? If you just pick a direction on the surface, you've digitized the surface. If I go back, so when we've sampled our surface, we've either oversampled it, so we've got overlapping spots that we've measured. We've put the spots that we're measuring adjacent to each other on the surface, or we've got some space in between them. Or if we have a raster scanning type instrument and we're in a hurry, we've put some space in between them in this direction. We've put a lot of space in between them in this direction. And now you don't have a characterization of the 3D topography anymore. You have a series of profiles on the 3D topography, but the software is going to treat it as if it was a characterization of the topography on the surface. So those are things to watch out for as you're doing the measurements. But as we've sampled the surface with whichever sampling strategy we've had, in the measured surface, so in the bit that the software can deal with, so we've measured some height in this region, and we plot it as a point that's in the direct center of that region, typically in the software. So as we do that, if I want to take my profile in this direction and my profile in this direction, if I've got a smart sampling strategy, when I've measured the direction, my sampling interval in those two directions is the same as each other. So I've got even spacing this way and this way. So that's an easy comparison to make. We make the analysis in one direction, we make the analysis in the other direction. We can compare that. Now we've got two data points. If we want to go at the 45-degree angle, now the sampling interval, the minimum distance between points that I've actually measured, has become square root of 2 times the square root of 2 times my sampling interval, right? So I've got to get the angle. If I pick another angle and I want to only use a measured point, now I'm at this angle. If I want to go only use another point and I want to get another angle, I'm out here. So you can see that you quickly reduce the resolution of your measurement by going to all these different angles. If you simply, and if I pick this point anyway because computers can interpolate, the interpolated point is always less than, it can't be greater than the adjacent points, right? It's always going to be less. So you reduce the complexity by interpolating. You reduce your ability to quantify the complexity by interpolating. So the algorithm we developed for the work with the anthropologists only took measured points. And we figured out if we did 18 directions on the surface in one quadrant, that we would decrease the sampling interval by a factor of 10. So you have to limit now the smallest. So when you do the length scale analysis, oops, this way, on those profiles, the smallest scale that we can go to in order to have comparable numbers with each other is 10 times whatever the minimum spacing was between the points that you measured. And if you're doing that analysis at smaller than 10 times the the spacing of the points that you measured, you're going to end up with strong directionality at 90 degrees, at 45 degrees, at 0 degrees when you run this analysis. So it's going to flaw your data at the finer scales. So that's something to watch out for. What do I got? Nancy's coming in 15 minutes. All right. The directionality, or the length of the profile also can be related to the scale. And we can do I want to do this? Chris is talking about this. I'm assuming you knew that it was open for questions at any time, but this would be a good time to open up for questions. No? I had questions for you and you answered. No questions for me? So those of you that, so who had seen the description of the length scale tiling before? The length scale analysis, so the basis. So you guys had seen this before. I know what Chris is doing in the other room is an introduction to surface metrology and principles. I don't know that he's going to touch on the area scale analysis, and we've got a little bit of time left before Nancy gets here. So what we can do is we can go through and we can look at the area scale method that was developed. So we used a conjunction of the area scale method and the length scale directionality in order to figure out what our ancestors were eating for that paper in Nature. So it depended. The length scale, the directionality will show if there's scratches on the teeth. So if you have a strong directionality on the surface, there's lots of scratches on the teeth. If you have a high complexity aerially, it's going to show that there's pits on the teeth. So that was the rationale there. So what I'll do is I'll talk a little bit about the area scale fractal analysis. We looked just at the length scale analysis before. At the area scale, we can do something similar to that Richardson tiling, but on a 3D topography instead of on the 2D profile of the surface. And so what we do is we take little triangular tiles, and we see how many of these triangular tiles can we fit on the surface. We calculate the area of one triangle. So each triangle has the same area. The shape is allowed to vary just a little bit. And again, you add up the total area of all the triangles. You divide that by the projected area onto a flat plane, and you've got a relative area plot now instead of the relative length plot. And again, we see there's a little periodicity in this surface. We've got a long linear fit, so this is the complexity. This is the rough region on the surface. And we note that here the complexity has changed. And so this is interesting. If we go back and look at the surface, so this is a diamond coating on a silicon substrate, and it was measured with an atomic force microscope. So as you get on the diamonds sitting on top of the diamonds, we're in this region of growing area on the surface, so as the tiles get smaller and smaller. When we get to this section here, our tiles are actually sitting on the facets of the diamonds. So we're not getting as much additional area as we go there because those facets are smooth. So at a very fine scale, if you were only looking at one facet on the diamond's not very rough. As it's a pile of diamonds sitting on top of each other, you've got a very rough surface. So you can look at this change in complexity, can tell you about things that are happening on the surface. Yeah.
But you lose information about directionality. This tells you, I mean, this makes a 1D measurement in that metric, right? You don't know direction anymore. Oh,
yeah, this is, yeah, we've lost direction in this case.
Is this used to scale degree when you look at a light scale measurement? How do you decide what is a significant amount of directionality if you look at two directions?
So if we're looking just at just two directions, or we picked the 18 that I picked out, it's going to depend on the interaction that you're trying to predict, I think. And there's more work that's needed to be done on that. So so what's a big number is the question.
How do you, I mean, I understand there may not be a single value for that discrimination, but how do you decide that this is actual directionality, not just, happenstance?
So one thing that we've seen is actually the work that I did in my master's trying to figure out this thing with the instrument with 3M, was that all the measurement devices by their nature put directionality into the measured surface. And I can go back to, I've got an interesting slide. So the instrument that we were using for the 3M measurements was a triangulation laser sensor on a raster scanning set of stages that could be held above a surface, so it could scan above the surface and make a surface map. The nature of that sensor was that there was light coming down, reflecting off the surface, scattering off the surface, and there was a detector offset at a 30-degree angle. So it could only see things that it could see from that angle, so it could never see the bottom of this valley, for example, in this orientation. If you turn the sensor 90 degrees, it could see the bottom of that valley. And so the way we did that study is we took the surface of interest and we measured it by scanning in this direction, so tracing in one direction, scanning adjacent traces in the next direction. Then in software, we just traced in this direction and scanned this way. So now we have two sets of data at the same region. Then we took the surface and turned it 90 degrees under the instrument, and we repeated that. So we had 8 sets of measurements. And if you want later, I can pull up the data and show you what we came up with. And so we were able to show, and then we did the analysis both along the tracing direction and the profile direction. And we were able to show that you could clearly group each measurement. So if the instrument were not putting any directionality into the measurement, you would have 4 distinct groups of points here when you did your comparison. And we had 8 distinct groups of points. So for each set of data, there was a grouping. And so we did that comparison. So I think if you want to know, is this change in directionality happenstance or is it from my instrument, you need to do a study like that just to see what's the noise floor on that instrument on that type of surface. And the jury's still out on what's a lot of direction and what's a little bit of direction. Intuitively, we see it, right? So we look at a surface and I say that's very directional. But as you look at how that direction changes with scale and how it's important, there needs to be more research and people need to do functionality studies. We've now developed a method that we can characterize how much direction there is, but I don't know what's a lot of direction. So I hope that helps. So and so what we did with the study looking at the fossilized teeth is actually kind of cool. They've got fossilized teeth and they've got teeth from apes that they had observed what they were eating, and they knocked out the apes before they took the impressions of the teeth, I think. So you've observed the apes, and then you look at these teeth look sort of like these teeth, and so they've been doing comparisons visually like this or with microscopes for years. And what we did is we said, well, if we look at how much directionality there is on the surface, we can do our 18 directions and we can say this is a highly directional surface relative to all the other ones. And this is a not very directional surface relative to all the other ones. And with that, we also looked at the area scale complexity. Oop, wrong way. It should just know which slide I want, right? Is there an app for that? So when we look at this area scale complexity graph, we actually did a plot of the directionality versus the complexity for each of those surfaces, and we were able to group together. So there was surface in groupings over here. The apes were like these fossils, and there was groupings over here where the apes eating something else were like these fossils. So that's how they made that determination. But it was a relative. So these are highly directional relative to the other ones. I don't know that there's a big this is direction answer. And I think Nancy Burnham is about to start. She said she was going to be here at 9:30, and she's going to do the second half of this 45 minutes talk. And she had a choice for you. So I can pull up the two choices for what she was going to talk about. Oh, and I just wanted an excuse to put my boat on the screen. What I'll do... So if you want to take a chance to get some water or something, feel free. We'll get restarted here again in just a second. And this is the only session of the whole 2 days where we're splitting in the middle with two different speakers. It's because one of the speakers at the last minute had actually two of the speakers at the last minute had a crisis. This one we knew about just a little bit before, so I took it. And the last one we found out yesterday. I think Chris must have mentioned that in the opening remarks. Yeah. So I apologize for being a little bit disorganized. I think I've worked out a few of the troubleshooting things that I'm going to need to fix in the other rooms. Yeah, I know. So we'll have, for my presentation, anybody that wants copies of the slides or anything, I'll have those available up at the check-in desk, and you can download them onto a USB key. And we'll ask all the presenters if they're willing to do that. Some of the presenters make their living by selling the thing that they're talking about today, so they probably won't want to do that, but we can...
So Toby,
yes.
As you sweep
through my 18 directions
across the various directions, if you plot the array of whatever parameter you choose to use.
you can measure any parameter. Absolutely.
As a function of the angle.
The one we chose here was to use the complexity, but you can choose
so
any.
You choose whichever.
Yeah.
Right. Okay. Is that a reasonably so it's not an analytic function, but it's what's the term? You get a continuous plot. If you pick a parameter and you just do a plot as a function of angle.
So we would then typically we would plot it on like a rosette plot, so on a polar coordinates, so that it looks like this. But it's because you have distinct points. It's a digital signal, but absolutely.
So theta is
and with the study on the teeth, because the fossilized teeth came out of the ground, nobody knew what the original orientation was for the mechanics of using, so we couldn't control for the original orientation.
Right, but
in a manufacturing process, you can control for orientation.
Right. But when you're looking at the data, you
you pick an origin, an angle, and then you just do
So
that.
yeah, with the teeth, we just picked a direction. You picked an arbitrary zero plane, and then we just looked at how much directionalness is there.
Right.
When we've looked at grinding wheels and dressing wheels and surfaces that have been ground, those have clear direction from the manufacturing process that we're expecting.
Yeah.
So there we would line up one of the 0 or the 90
Although
with one of those.
The grinding wheel itself should not before it's been dressed.
Before it's been dressed, yeah. We were looking at already been dressed wheels.
Okay.
we were doing a study on dressing and looking at the directionality. So Nancy, I think you can jump up and you have the opportunity of being videotaped or not.
No.
So I'll go ahead and turn off the mic.